GameSci.com. GameSci.com.
How you doing? Welcome to lesson on RedBlack trees. They are a balanced binary search tree data structure. Over here on the left, we have a balanced binary search tree. This operates at full speed, order of log n. You can see there's a maximum of 4 levels down this side of the tree and a maximum of 4 levels down that side of the tree. 4 levels per side of the tree. This is a balanced binary tree. Compare it to the tree on the right. This is an unbalanced binary search tree. The performance of this tree can degrade towards order of n. As the tree becomes more unbalanced, it takes longer and longer to search down this side of the tree. Red-black trees, how are they different? First and foremost, red-black trees are a set of 4 rules that help maintain a balanced tree. The rules are coming soon. Let's review binary trees first. Bi means 2. Binary trees can have at most 2 children. 50 has 2 children, 25 and 70. 1 child is okay. 80 has 1 child, 75. And of course 20, the leaf node, has no children whatsoever. A binary tree can have 2, 1, or 0 children, but no more than 2. Not all binary trees are search trees. Notice how all the values to the left of key 50 are smaller than 50. Everything on this side of the tree is less than 50. Notice how all the values on the right of key 50 are bigger than 50. Everything on the right side is larger than 50. That's what makes this a binary search tree. Any node with a key value of x, all the keys in the left subtree are less than the value of x, and all the keys in the right subtree are greater than the value of x. A red-black tree is a balanced binary search tree. It is a tree that is not only less than and greater than, but it guarantees balance throughout the life of the tree. To review some terms for binary trees, a node is where the data is stored. Each circle in this tree represents a node. So 70 is a node, 60 is a node, 80 is a node. Key is the most important data. It identifies the node and is used in the less than or greater than rule. This key 25, everybody to the left is less than 25. Everybody to the right is greater than 25. 50, 25, 70 are keys pictured in the red-black tree nodes. The root of the tree is the top of the tree. All the searches, inserts, and deletes start at the root. 50 is the current key in this root. A leaf is at the bottom of the tree. Leaf nodes do not have children. 10, 20, 40, 60, and 75 are all leaves of the binary tree. Level. The root is at level 0 of the tree. 25 and 70 are at level 1 of the tree. 15, 40, 60, so on are on level 2 of the tree. And finally 10, 20, and 75 are on level 3 of this tree. Related to level is the height of the tree. The height of this tree is 4. If the height of the tree is 4, the levels are numbered 0, 1, 2, and 3. Some new terms to learn with red-black tree. Grandparent. 70 has a child of 80 and a grandchild of 75. 70 is considered the grandparent of 75. Parent node. 80 is a child of 70, but also a parent of 75. And finally, a child node. We all know what that is. 75 has a parent of 80 and now a grandparent of 70. A couple more specific terms as it relates to grandchildren and grandparents. 10 is considered the outside grandchild of 25. 10 is the outside grandchild of 25, and 20 is considered the inside grandchild of 25. 20 is the inside grandchild of 25. Here are the red-black tree rules. This is what you have to know in order to implement red-black trees. Number 1, a node is red or black. Number 2, the root is always black. Number 3, a red parent must have black children. And number 4, every path, root to leaf, must contain the same number of black nodes. Any red-black tree where all 4 rules are true is balanced. All 4 rules are true on the tree above. This is a balanced red-black tree. The 4 rules also assist the insert and delete algorithms in maintaining that balance. The colors are there for a reason. It allows or instructs the algorithms on how to balance the tree. Looking at the rules in detail. Number 1, a node is red or black. There's a black node, there's a red node, there's a black node, there's a red node. I don't see any purple nodes, do you? Rule number 1 is true. All nodes in this tree have a color of red or black. This could be a simple boolean or bit in the node that indicates the color red or black. Seems like a trivial rule, but the color is critical to the insert and delete algorithms to determine the changes needed to maintain the balance. The colors instruct the algorithms how to balance this tree. Rule number 2, the root is always black. This rule is trivial. The root has got to be a black node at all times. But there are operations like color flips and rotations that may change the root color. Change it back to black immediately. Rule number 2 is true in this tree. Rule number 3, a red parent must have black children. Emphasis on parent in this rule. Note, 25 and 70 are the only red parents. 25 has 2 children, 15 and 40. 70 is a red parent. 60 and 80 are its children. Their children are black nodes. Rule number 3 is true in this case. Notice, however, that 10, 20, and 75 are red, but they're not red parents. Rule number 3 does not apply to 10, 20, and 75 because they are not parent nodes. Rule number 4, every path, root to leaf, must contain the same number of black nodes. Every path, root to leaf in this tree contains 2 black nodes. What are we talking about? If you go down this path of the tree, you have passed through exactly 2 black nodes, 50 and 15. Pass through 50 and 15 to get to 10. You pass through 2 black nodes, 50 and 15, to get to 20. And that applies to every path in the tree. You pass through 50 and 40 to get to 40. You pass through 50 and 60 to get to 60. Every time, every path, we're going through exactly 2 black nodes. You'll even pass through 2 black nodes, 50 and 80, to reach 75 or 80. Rule number 4 is true in this case. That means all 4 rules are true for this tree. This is a red-black correct tree, and it is a balanced tree. When these 4 rules are true, you can bet you have a balanced binary tree. The first 2 rules are easy. Each node is red or black. The root is always black. Those are the simple rules. They're simple and easy. The key to understanding red-black algorithms is rules number 3 and 4. Basically, what rules 3 and 4 do is it sets up a black, red pattern all the way down the tree. Once in a while, you can get some black runs in it, but for the most part, we're talking about a black, red pattern. The color patterns tell the algorithms when and where to do color flips and rotations. And color flips and rotations are the things we do to turn the tree red-black correct and to make the tree balanced. Rules number 3 and 4 are a catch-22 on an unbalanced tree. On an unbalanced tree, you cannot fix rule number 3 without breaking rule number 4. And you cannot fix rule number 4 without breaking rule number 3 for an unbalanced tree. The two rules contradict themselves, and you can't fix one without breaking the other on an unbalanced tree. As the algorithm does color flips and rotates to maintain the color pattern, it will balance the tree for you. And you'll know it's balanced because all 4 rules are true. The only way you can get all 4 rules to be true is to balance the tree. RedBlack insert and delete are one-pass algorithms. As we're working our way down the tree, we will fix the tree so we can insert at the bottom and not domino back up the tree. What we're going to do is color flips and rotates as you move down the tree, inserting a new item like 22. You will be changing the colors of the nodes. You may be rotating the nodes. You'll be modifying the tree as you work your way down. By the time you get to the end of the tree, you just insert the new node. Make changes on the tree on the way down the tree, preventing a domino effect where it has to move all the way back up the tree to rebalance after the insert or delete. The goal is to fix the tree on the way down. By the time we do the insert, it slides into a balanced tree. Know the 4 red-black rules. Number 1, a node is red or black. Number 2, the root is always black. Number 3, a red parent must have black children. Number 4, every path, root to leaf, must contain the same number of black nodes. When all 4 rules are true, the tree is red-black correct, and the tree will be balanced. When all 4 rules are not true, operations like color flips and rotations are used to make the tree red-black correct and therefore balanced. Red-black color flips and rotates. Follow the rules to build a red-black tree. After we look at a few red-black tree basics, we'll build a tree from scratch and see how the rules balance the red-black tree as it grows. Red-black algorithms are one-pass algorithms. As an insert works its way down, it will modify the tree in 3 ways. Number 1, color flips on the way down. Number 2, rotations after a node is inserted. Number 3, rotations on the way down the tree. The algorithms change the tree so that when a new node is inserted, the tree is balanced. There are many ways to represent a red-black tree in computer program. It is, after all, just a specialized binary search tree which stays balanced. What we'll look at is one way of implementing a red-black tree in RAM memory. Package RB tree. Set up a package RB tree so the class RB node can allow access to its variables to class RB tree. Note the lack of public and private on the variables. This is called default access. This is intentional. I'm not going to declare in private. I'm not going to declare in public. Therefore, everybody else in the same package has direct access to these variables. We're going to implement 2 classes here, RB node and an RB tree, and we want RB tree to have access to these variables. Public class RB node. This is an object-oriented approach. Each element in the tree will be an RB node object. Everything in a circle is an RB node object. We'll then use references to connect the RB nodes. Those are the lines. Each of the line between these nodes is a reference to another RB node object. Use references to connect the nodes, similar to the link objects in a linked list. Basically, we're going to implement this as a double-headed linked list. The root has 2 linked lists, a left linked list and a right linked list. 70 has 2 linked lists, a left linked list and a right linked list. This is the left reference from 80 to 75. And of course, 75 is an RB node object, as well as all of these other circled elements. All of these are RB node objects. Int key. The key is critical. It follows the less than, greater than rule and may uniquely identify data in the RB node. 50, 70, 40 are all keys. It's not always an int. The key could be string email or a long phone number. I use ints in my examples, and most books use ints in their examples because ints are easy to understand. It's very simple to do a less than and greater than on an int. We're logically showing you how a red-black tree is set up using ints, but there's nothing about a red-black tree that insists the key has to be an int. Anything you can compare and determine less than and greater than can be used as a key to a balanced binary tree. This is new. Boolean is red. A required Boolean or bit to determine node color is used by algorithms to determine how to balance a tree using black-red pattern. Note in 70, the isRed Boolean variable must be true. And for node 40, the isRed Boolean variable must be set to false because 40 is a black node. Once again, 20 is a red node, so the isRed field in this object must be set to true. This is how we determine the color of a node, and since it's a true-false variable, every node will be red or black. When this is true, it is a red node. When this is false, it is a black node. RB node left. The left reference points to all the items that are less than the current RB node keyed. Makes it easy to move subtrees and easy to check the color of a child. If you go to the left child and check the isRed field, if it's true, you know the left child is red. If it's false, you know the left child is black. Inside the node, there is a left reference. I can go to the child and check to see if it's red or black. RB node right. The right reference points to all the items that are greater than the current RB node keyed. Makes it easy to move subtrees and easy to check the color of a child. I've got arrows here on right references. The right child of 50 is this line right here to 70. The right child of 70 is this reference right here to the node 80. The right child of 25 is this reference to the node 40. When I want to check what color 25's right child is, I can go to right.isRed and I'll go to the right child, check the isRed field. It's false, so it must be a black node. In 15, its right child.isRed would take me to this node. IsRed would be true for that node. I would know that the right child of 15 is red. Earlier we saw a slide on the 3 changes that happen as you're moving down a red-black tree to keep it correct. Change number 1 is a color flip on the way down. When an insert finds a black node with 2 red children, it changes the color of all 3. See the before and after picture below. It does not change the black height. You still pass through one black node as you traverse through 15, 10, or 20. Also, adding a new red leaf won't break rule number 3. New nodes default to red because they do not break rule number 4. There is a critical assumption that is made. On a red-black insert, the new node is always red. So one of the things the color flip does is it prepares for inserting a red node. Let's look at the before picture. Notice how I have a parent that is black with 2 red children. When the insert sees a parent that is black with 2 red children, it's going to flip the colors of all 3. Here's the before the color flip. Here is after the color flip. 15 went from black to red, 10 went from red to black, and 20 went red to black. That is an always. That happens every time it sees a black parent with 2 red children. Let's look at the code that does this color flip. The if statement says when I'm black, that's 15, checking this, and my children are red, 10 and 20, the condition is true and we need to do a color flip. This is the before state of the 3 RB nodes. Is red is false. Is red is false is very much true for this statement. And my left child is red. Well, that is also true. The left child of 15 is red. And my right child is red. That is also true. The right child of 15 is red. All three of these statements have to be true. Current node 15 is not red. The two children are red. I've got a black parent with two red children. When that happens, I need to color flip all three. After the flip, this is the color of the nodes. I'll go to 15 and say your is red flag is true. Turn 15 to a red node. I'll go to the left child and say your is red flag is false. And I will color flip 10 to black. I'll go to the right child and say your is red flag is also false. And I will color flip 20 to black. This is the before picture, black parent with two red children. This is the after picture, red parent with two black children. Every time the insert algorithm sees this color pattern, it performs this color flip. The third change we can make to a red-black tree as we're working our way down the tree is to rotate on the way down. Change number 3 is rotate on the way down. When a color flip creates a red parent with a red child, it indicates a rotate must be performed. Rule number 3 has been violated. The black, red pattern needs to be fixed. A rotate left or right will restore the pattern and allow a new node to be inserted without unbalancing the tree. This is the genius of the red-black tree. It predicts when the insert at the bottom of the tree will unbalance the tree, so it rotates before it reaches the bottom and prevents the new node from causing an unbalance. Here's the color pattern before I do my color flip. Red, black, red pattern is intact. When I see this black parent with two red children, color flip says flop those colors. My black parent becomes a red parent. My two red children become black children. This causes in the box a red parent with a red child. I just violated rule 3. They cannot have a red parent node with a red child. What we need to do now is rotate. Follow the rules to build a red-black tree. Change number 2 is rotate on the bottom. When a leaf insert creates a red parent with a red child, it indicates a rotate must be performed. Rule number 3 has been violated, and node 10 clearly sticks out and unbalances the tree. A rotate right will raise 10 and restore balance to the tree. This is the before picture. 10 is sticking out and creating an extra level. There are 4 levels on this side of the tree and only 2 levels on that side of the tree. We need to rotate some data to balance this tree. The grandparent node of 25 rotates down and right and changes color to red. The parent node 15 rotates up and right and changes color to black. Finally, node 10 rotates up and right, reducing the number of levels of the tree and balancing the tree. Here's what the tree will look like after the rotate. Now we'll step through this rotate one by one so you'll understand it a little bit better. But that's basically what a rotate does. Anything that sticks out, you can rotate it back up into the middle of the tree and rebalance the tree. Let's build a red-black tree from scratch. Remember, new nodes default to red, but since this is the root and rule number 2 says the root must always be black, it immediately changes it to black. And you see I have a black root of 50. Building the red-black tree from scratch, add node 40. New nodes default to red because they do not immediately break rule number 4, the black height. This tree does not violate any rules. It is red-black correct and balanced. New nodes default to red. Add node 70. New nodes default to red because they do not immediately break rule number 4, the black height. If I put a black 70 here, it would definitely violate Rule 4. There'd be 2 black nodes on this path and only 1 black node on that path. New nodes default to red at all times. This tree does not violate any of the red-black rules. It's red-black correct and balanced. Add a new node 25. But color flip first. Huh? When insert encounters a red parent with 2 red children, it will change all 3 colors. Since the root has to be black, after it color flipped to red, it immediately changes back to black. Red-black trees change as it works its way down, so when a new insert of 25 occurs, it doesn't violate the 4 rules. The new insert of 25 is not quite done yet. The color flip happens before the insert. This was black, red, red. I did a color flip, changing these colors, and of course I had to change the root back to black. The red-black trees are one-pass algorithms. We will pass through the data once on our way to inserting 25. Completing the add of node 25, it's less than 50, so we went to the left. It's less than 40, so we went to the left. Thanks to the color flip on the way down, notice all 4 rules are currently true. Number 1, all nodes are red or black. Number 2, the root is black. Number 3, red parent, black children. There are no red parents, so that is true. Finally, number 4, the black height is 2 down every path. 2 black nodes to get to 25, 2 black nodes to get to 70. This tree is red-black correct, and it is a balanced tree. Add node 15. It makes it to the leaf without a color flip, but after the insertion, there is a violation of rule number 3. A red parent cannot have a red child. This signals a rotate right is needed to correct the red-black rules and balance the tree. The rotate right will be done in several steps to illustrate how it works. We're still adding node 15. Triggers a rotate after the insert. Node 40, the grandparent to the new node 15, rotates down and right and changes color to red. The insert rotate is not done yet. We still have 2 more steps. This is step 1 of the rotation, where 40 rotates down and right and changes color. Still adding node 15. Rotate after the insert continues. Node 25, the parent of 15, rotates up and right and changes color to black 25. The insert rotate is not quite done. There's still 1 more step. But you see this 25 right here? It rotated to the right and up and changed its color to black. Still adding node 15. Rotate after the insert continues. Node 15, the child that broke rule number 3, rotates up and to the right. The insert rotate is done. All 4 rules are now true on this tree. It is red-black tree correct and balanced. Notice how I pass through 2 black nodes to get to every node. 2 black nodes there. Notice how I do not have any red parents with red children. That's what a rotate does. It rotated the thing that stuck out up into the middle of the tree and rebalanced the tree. Add node 80 as the right child of 70. Not all inserts cause color flips or rotates. As it worked its way down the tree, there was no need for a color flip. There was no need for a rotate. Also, you can see why we default to new nodes being red. Adding a red node here does not violate Rule 4. But when needed, algorithms will change the tree so it stays fairly well balanced at all times. Know the 4 red-black tree rules. When all are true, the tree is red-black correct and balanced. The rules are, number 1, a node is red or black. Every node in this tree is red or black. Number 2, the root is always black. The root here is black. Number 3, a red parent must have black children. There are no red parents, so rule number 3 has to be true. Number 4, every path root to leaf must contain the same number of black nodes. 2 black nodes to get to 80, passing through 2 black nodes to get to 40, passing through 2 black nodes to get to 15. All 4 rules are true. This is a red-black correct tree, and it is balanced. Red-black trees operate at order of log n speed by staying well balanced at all times. Even when it must rotate in the middle of the tree, it still makes just one pass down the tree. There's no domino effect with red-black trees. Also, remember your power of 2 arithmetic. Let's say you have a red-black tree with 65,536 items in it. Well, if you know your powers of 2, 2 to the 16 is 65,536. Log base 2 of 65,536 is a 16. That means our tree has roughly 16 levels, and in a find or insert, we'll only need to examine or change 16 nodes. What if you double the number of items to 131,072? Only 17 nodes need to be examined or changed. You can double the number of items in the tree, but only add a single level to it, which means your algorithm takes slightly longer, but not that much longer. That's what order of log n means. As this tree gets bigger and bigger, it will take slightly longer to search the red-black tree. And that's the advantage of a balanced tree. You know how many levels each side's going to have.
GameSide.com.